Hello, my name is Kunle Olukotun, and I'm the co-founder and chief technologist of SambaNova Systems. The title of my talk is Accelerating Software 2.0. At SambaNova, we are developing the next generation of systems for machine learning applications, and these are being driven by three computing trends. The first is that multi-core processing utility is running out of steam. And this is true whether we're talking about fat cores on a CPU or much more efficient thin cores on a GPU. And this is driven by the declining slowdown of Moore's law. And so what we need is a much more efficient set of architectures for providing performance for machine learning for both training and inference. The second trend is the convergence of training and inference. There are lots of benefits to be had by accelerating both training and inference on the same piece of hardware. And lastly, what we see is that the fundamental ideas that we are exploring in SambaNova of exploiting data flow processing are applicable to lots of applications beyond machine learning. As we see the widespread use of machine learning in the form of deep learning and neural networks, this has the potential to fundamentally change the way that we develop software. So before machine learning, we developed what we're now calling software 1.0. And here, code is written in C++ or some other high-level language, and it requires domain expertise to decompose the problem and to design algorithms for the different components and then compose them back together. Contrast that with software 2.0. This term was coined by Andrej Karpathy. And here the idea is that you train neural networks using training data. And the program is written in the weights of the neural network. This has a number of advantages. The key one is that you have a reduced number of lines of code that actually have to be explicitly developed by the programmer. This is an example of this is Google's Translate. They shrank their code from 500,000 lines of imperative C code to 500 lines of Dataflow code written in a language called TensorFlow, which is a domain-specific language that is used by many machine learning algorithm developers. And what we see is if we look at the development of machine learning applications, they're done using these high-level frameworks like TensorFlow and PyTorch. And these frameworks generate a data flow graph of machine learning operators like convolution, matrix multiply, batch norm, and the like. And what we've shown from some research that we did at Stanford was that you could take these domain-specific machine learning operators and convert them into what we call parallel patterns. And these parallel patterns express the parallelism and locality in the application and can be optimized for higher performance. And what we see is not only can these operators, these parallel patterns represent machine learning applications, they can also be used to represent the operators in SQL that is used for data processing operations. And these can be represented efficiently using parallel patterns. So what we see is that the next generation of software 2.0 systems require a number of things to be supported very efficiently. One is hierarchical parallel pattern data flow, which is a natural machine learning execution model and is natural for a number of other types of computation, such as SQL. The other thing is support for very large models, terabyte-sized models that provide much higher accuracy on applications. A third need is to support sparsity. As we try to model the real world in more fidelity, graph neural networks are a key element of this, and sparsity is required to run these networks efficiently. Also is required is support for flexible mapping of these machine learning graphs onto the underlying hardware. And this could be by taking advantage of model parallelism within the network or data parallelism across different input inputs, different data inputs. And lastly, the need for supporting data processing. And here we're talking about SQL sorts of operations, as these are going to be or will be a key part of machine learning training. So the architecture that we've developed to efficiently support all these requirements for software 2.0 is called the Reconfigurable Dataflow architecture. And what this architecture does is it natively supports hierarchical parallel patterns. And the way that it does this is by a set of configurable units. We have the pattern compute unit, PCU, where the computation takes place, and the pattern memory unit, which provides configurable memory to support high performance computation. And these components are connected together, are scaled or tiled across the chip and connected by a flexible on-chip communication fabric. And the first implementation of the Reconfigurable Dataflow architecture is the SambaNova system's Cardinal SN10 RDU. And this is a RDU chip that is implemented in the latest TSMC technology, 7 nanometers, has a total of 40 billion transistors and over 50 kilometers of wire. It provides hundreds of teraflops of computation capability for accelerating machine learning applications, and also hundreds of megabytes of memory that is closely coupled to this computation to provide the data and the weights for these machine learning networks. In addition to what's on chip, we have very efficient off-chip interfaces, both to terabytes of memory and to other RDU chips. So if you look at the benefit of this reconfigurable data flow approach, it provides unprecedented flexibility. When thinking about designing high performance applications, one has to balance both computation and communication. And in traditional architectures, such as CPUs and GPUs, that gave you the ability to program the compute in a very flexible way, but it didn't give you the ability to program the data flow very efficiently. And so with the Reconfigurable Data Flow unit, we provide capabilities to both control and program the compute and the data flow between this compute. And this flexibility provides an order of magnitude improvement in performance across a range of applications, or it makes some applications possible that were not possible before. If we look at how the Reconfigurable Data Flow architecture provides support for machine learning graphs, this is what we see is that the key to this flexibility is the ability to map these graphs in a spatial manner onto the chip, as shown in this figure. Here we see that the PMUs provide the local data access for input data and weights, and the computation is done inside of the PCUs. And the communication between the different kernels is provided very efficiently by the on-chip interconnect. And the impact of doing this is a dramatic reduction in off-chip bandwidth and consequently very high utilization of the compute. And as we know, it's not just about peak compute, but it's about how efficiently this compute is used, and the data flow capability of the RDU gives you very high efficiency. So the heart of the SambaNova systems is the RDU chip, but the full capabilities of what we've developed at SambaNova are unleashed by providing a fully integrated system of chips and memory and host interfaces. And this is all packaged in a system that is completely integrated and provides the ease of deployment that enables users of the SambaNova system to get to the results as quickly as possible. And so we provide high performance, scalability, and we have the initial systems are an 8-socket data scale system called the SN10-8, and that's a quarter of a rack. and then each of these systems can be connected together, 4 of them to a rack, to create a data scale SN10 8R full rack system. And both of these systems are fully integrated and ready to go when they are delivered. In order to develop applications for these systems, we start with open source frameworks such as PyTorch or TensorFlow. And these frameworks generate a graph of ML operators that we've already shown. And then this graph is optimized and transformed into a set of lower level ML operations. These operations form their own Dataflow graphs, which are further optimized and mapped spatially to a single RDU chip, or potentially even multiple RDU chips. And the mapping is flexible. As I said, it could be a model parallel type of mapping, or it could be a data parallel type of mapping. The optimizations that take place include tiling to optimize the use of the memory on chip, streaming, so to allow data to be streamed from one operator to another efficiently on chip, and nested pipeline and parallel operations to take advantage of all the computational capability on the chip. And so you can achieve very high performance directly from the high-level ML frameworks using Python without having to meet the need to develop custom operators in a low-level language like CUDA, because the performance you get out of the box from the frameworks is already very good. So what we are delivering then is a very disruptive way of providing very high performance using this data flow approach. But because we deliver it in a package which is familiar to the developers of machine learning applications, it makes it very easy to digest, right? We're using standard rack form factors, standard power and cooling, and the software interfaces are the standard open source frameworks that everybody is familiar with. And so you can get going using these existing standards, and it gives you a fast time to results. So what kinds of capabilities is the SambaNova system unleashing? Fundamentally, what we want to do is enable capabilities that are not possible with conventional architectures, such as how do you, on a single system, provide very large natural language processing models. Natural language models are kind of the key to knowledge and understanding, and so building bigger models gives you higher accuracy and better knowledge, and we are shooting for trillion parameter models. Another area that we are unleashing and making capable that's not been possible before is the ability to do very high accuracy model development for high resolution models, right? So 50K by 50K resolution. This enables, interesting applications in astronomy, medical imaging, X-ray imaging for viruses, all sorts of things that are not possible today or are possible with limited accuracy. Here we're giving you full resolution accuracy models. A third area that the SambaNova systems will make available is the idea of building very large recommendation models. And these are models with tables that exceed 100 gigabytes, which are bigger than is possible with conventional GPUs. And providing, so what we would do is be able to provide very high performance for these kinds of embeddings and these kinds of models, and provide both the compute capability for doing the multi-layer perceptron component of the algorithm, but also the ability to handle very large embeddings. So let's take a slightly deeper dive into what we're making possible in the natural language processing area. If you look at the models that are being developed in the natural language processing area, they're evolving in two directions. One is the idea of more detailed models with richer contextual information to provide higher accuracy. And the other way that they're developing is much larger models with many more parameters in order, again, to provide higher accuracy. So the problem is that the constraints of the current training architectures, hardware like from GPUs, constrains what you can do in these two dimensions. So to show what's possible with SambaNova, we look at a three-layer BERT model that was developed at Microsoft and is being deployed at Bing, and it provides richer context compared to conventional BERT NLP models. And it turns out that we can take this idea and have fewer parameters in each of the encoders, but stack them more deeply. And this will give you higher accuracy. So our accuracy improves from a QNLI score of 78.7 to 79. And if you look at the performance that we achieve on the RDU, it's 6x faster than you can achieve on the GPU. So this shows that we can take advantage of this richer contextual information and also give you higher accuracy and higher performance at the same time. Another dimension, as I said, that natural language processing models are evolving in is the idea of a larger number of parameters, right? The whole idea is that by increasing the number of parameters, you can get a more accurate model. And so the practitioners in the NLP space are pushing the size of the model that's being developed. In the beginning of the year, Microsoft came up with a idea for training models on large numbers of GPUs. They called it Zero, and they showed a 17 billion parameter model. A few months later, in March, SambaNova Systems came out with a training method that we call One, and this allows us to train on a single system 100 billion parameter model. More recently, Microsoft has increased the size of their models to 170 billion parameters, and we are working on a trillion parameter model. And the nice thing about the approach that we're taking with SambaNova is that we can use the same way of programming the model to scale from a 10 billion parameter model to a trillion parameter model. So you don't have to change the programming model, but yet you are able to train these very large models, and you can do it with a much smaller system because we can train these models so much more efficiently, and we have the capability of handling much larger memory. And so if you look at what it took to get to the size model for the Microsoft work, they required 64 DGX2s, 1024 V100s, and we could do the same sort of model training on a quarter rack containing 8 RDUs and 12 terabytes of DRAM. So not only are we improving training, but we are also thinking about how to do inference very efficiently. And here today, training is done on GPUs, which are efficient for large batch sizes, and inference is done on CPUs, which is efficient for batch one. So with SambaNova, we are as efficient at large batch sizes as we are for batch one, and so that gives us the capability of doing things like inference that is periodically, where we dynamically refine the model by training while we're doing the inference. And so the benefit of doing this is that we can do very efficient high throughput inference. So this example shows with with the same three-layer BERT model that we already talked about. Here we have the ability to halve the latency and increase the throughput 16 times over what is possible with a GPU. And in this case, we're using a batch size of 1, whereas the GPU is using a batch size of 4. So this is much more inference friendly. If we look across the HPC workload space, and if we look to medical imaging, we'll see that many of the workloads have this data flow characteristics and could be accelerated by an RDU. And so we're currently looking at all of the different ways that we can adapt these sorts of applications to the RDU. And these applications include traditional data processing applications like SQL. And so, as we said, the RDU both gives you very high efficiency, but also high flexibility. So to conclude then, you look at these 3 computing trends, the multi-core architectures have run out of steam, and we're replacing it with the reconfigurable data flow architecture, which is implemented in SambaNova RDU. And this provides the capability to both do very efficient large batch training, but also single batch inference. So we can converge the 2 parts of machine learning onto the same piece of hardware. And because many of the applications that one wants to run are data flow applications, we'll see that such as scientific applications in material science and image processing, we see that SambaNova has the capability to provide general purpose acceleration beyond ML. So thank you.